Welcome to our channel. Today, we're diving into the mysterious and mind-bending world of black holes. These cosmic objects are some of the most extreme and fascinating entities in the universe, warping the fabric of space and time. Black holes have captivated the human imagination for centuries, inspiring wonder and fear in equal measure. We're going to unpack 5 fascinating facts about black holes that will illuminate their bizarre properties and profound influence on the cosmos. Get ready to be amazed by the sheer power of these gravitational behemoths. We'll explore how they form, what happens at their enigmatic event horizons, and the mind-boggling concept of a singularity. So buckle up and prepare for a cosmic adventure as we journey into the heart of darkness, where gravity reigns supreme. Black holes are born from the death throes of massive stars. Now, we're not talking about your average star like our sun. We're talking about stars at least 10 times more massive, true cosmic heavyweights. These stars live fast and die young, burning through their nuclear fuel at an astonishing rate. As they exhaust their fuel, the outward pressure from nuclear fusion can no longer counteract the relentless inward pull of gravity. Imagine a cosmic tug-of-war, with gravity ultimately winning the battle. The star's core collapses in on itself with unimaginable force, creating a region of space-time so dense that nothing, not even light, can escape its grasp. And just like that, a black hole is born. It's a cosmic graveyard, a testament to the immense power of gravity in our universe. Let's talk about the event horizon, a region surrounding a black hole that marks the boundary between our universe and the abyss. This boundary is not just a simple line or a visible edge. It's a complex and fascinating region where the gravitational pull becomes so strong that nothing, not even light, can escape. The event horizon is often referred to as the point of no return because once an object crosses this threshold, it is doomed to be pulled into the black hole's singularity. It's a cosmic point of no return, a place where the laws of physics as we know them break down. The event horizon represents a boundary beyond which our current understanding of physics ceases to be useful. Inside this region, the gravitational forces are so extreme that they warp space and time in unimaginable ways. The very fabric of reality is twisted and contorted, making it impossible to predict what might happen to anything that ventures beyond this point. Imagine crossing the event horizon. Time itself would seem to slow down for you as you approach this boundary relative to someone observing from a safe distance. This phenomenon known as time dilation occurs because the intense gravitational field of the black hole warps the space-time continuum. To an outside observer, it would appear as though you are moving slower and slower as you get closer to the event horizon, eventually seeming to freeze in time. In fact, from their perspective, you would appear to be frozen in time, forever hovering at the edge of the abyss. This is because the light from your spacecraft or body would be stretched to longer and longer wavelengths, making it increasingly difficult for an observer to see you. Eventually, you would fade from view entirely, becoming invisible to the outside world. But from your point of view, you would continue to fall inward, inexorably drawn towards the singularity at the heart of the black hole. The singularity is a point of infinite density where the gravitational forces are so strong that they crush everything to an infinitely small point. As you fall closer to the singularity, the gravitational pull would become more and more intense, pulling you faster and faster towards the center. As you approach the singularity, the gravitational forces would become increasingly intense, stretching you out like spaghetti in a process known as spaghettification. This is because the gravitational pull on your feet would be much stronger than the pull on your head, causing your body to be stretched out into a long, thin shape. The closer you get to the singularity, the more extreme this stretching becomes, until you are eventually torn apart by the immense gravitational forces. No spacecraft, no matter how advanced, could ever hope to escape the clutches of a black hole once it crosses the event horizon. The gravitational pull is simply too strong for any known technology to overcome. Even if a spacecraft were equipped with the most powerful engines imaginable, it would still be unable to break free from the black hole's grip. The event horizon is a one-way boundary, and once crossed, there is no turning back. It's a one-way trip to oblivion. The journey into a black hole is a journey into the unknown, a voyage into a region of space where the laws of physics as we understand them no longer apply. It's a place where time and space are warped beyond recognition and where the very fabric of reality is twisted and contorted. For now, black holes remain one of the greatest mysteries of the universe, a tantalizing glimpse into the limits of our understanding of the cosmos. So, we've traversed the event horizon, that point of no return. This is the boundary around a black hole beyond which nothing can escape, not even light. It's a region where the gravitational pull is so strong that escape velocity exceeds the speed of light. As we cross this threshold, we leave behind the familiar laws of physics and enter a realm of extreme conditions and unknowns. What awaits us now at the heart of a black hole? This is a question that has puzzled scientists and astronomers for decades. The core of a black hole, often referred to as the singularity, is a place where our understanding of the universe is pushed to its limits. It's a region of space where the gravitational forces are so intense that they warp the fabric of space-time itself. Well, hold on to your hats, folks, because we're about to explore one of the most mind-bending concepts in the universe: the singularity. This is the point at the very center of a black hole where all the mass of the black hole is concentrated. The singularity is a one-dimensional point which contains a huge mass in an infinitely small space, where density and gravity become infinite and space-time curves infinitely. Imagine, if you will, all the matter of a star, many times the mass of our sun, crushed down to a single point. This process begins when a massive star exhausts its nuclear fuel and can no longer support itself against gravitational collapse. The core implodes, and if the remaining mass is sufficient, it forms a black hole. The outer layers are blown away in a supernova explosion, while the core continues to collapse into the singularity. Not just a tiny speck, mind you, but a point with zero volume and infinite density. That's the singularity. It's a place where the known laws of physics cease to apply. General relativity, which describes the gravitational forces, and quantum mechanics, which describes the behavior of particles at the smallest scales, both break down in the face of such extreme conditions. Now, here's where things get really weird. The singularity is surrounded by an event horizon, beyond which we cannot see. The intense gravitational field distorts space-time to such an extent that it creates phenomena like gravitational lensing, where light from stars behind the black hole is bent around it, creating a ring-like appearance. At the singularity, the laws of physics as we know them break down. The equations of general relativity predict a point of infinite density, but this is a concept that doesn't fit within our current understanding of the universe. It's a paradox that has led scientists to search for a theory of quantum gravity which would reconcile the principles of quantum mechanics with those of general relativity. Space and time become so warped that our current understanding simply cannot describe what's happening. Time itself slows down as you approach the event horizon, a phenomenon known as time dilation. To an outside observer, it would appear as though time has stopped for anything falling into the black hole, while for the object itself, time continues normally. It's like trying to use a ruler to measure the circumference of a thought. Our tools and concepts are simply not equipped to handle the extreme conditions at the singularity. This is why black holes are such fascinating objects of study. They challenge our understanding and push the boundaries of what we know about the universe. It's a realm where the very fabric of reality is torn asunder. The intense gravitational forces stretch and compress space-time, creating what is known as a gravitational well. This well is so deep that not even light can escape, which is why black holes appear black. The closer you get to the singularity, the more extreme these distortions become. It's a place where the infinite density might even lead to a bridge connecting to other universes. Some theories suggest that black holes could be gateways to other dimensions or parallel universes. These are known as wormholes, hypothetical passages through space-time that could create shortcuts for long journeys across the universe. Or maybe it's something even more bizarre that we haven't even begun to conceive. The singularity could hold secrets that are beyond our current scientific understanding, revealing new aspects of the universe that we can't even imagine. It's a frontier of knowledge that continues to inspire and challenge scientists around the world. But that's the beauty of science. There's always more to discover. Each new piece of data, each new observation brings us one step closer to understanding these enigmatic objects. Black holes are not just cosmic curiosities, they are laboratories for testing the limits of our knowledge and expanding the horizons of human understanding. So we've talked about how nothing, not even light, can escape the immense gravitational pull of a black hole once it crosses the event horizon. This boundary, the event horizon, marks the point of no return. Once anything crosses this threshold, it is inevitably pulled into the black hole's singularity, a point of infinite density where the laws of physics as we know them cease to function. It's a one-way ticket to oblivion, right? The idea of a black hole is often associated with doom and finality, a cosmic abyss from which there is no escape. But is that really the end of the story? Well, it turns out the universe has a few tricks up its sleeve. The cosmos is full of surprises, and even in the seemingly hopeless scenario of a black hole, there are fascinating phenomena at play that challenge our understanding of the universe. Even in the face of a black hole's ultimate darkness, there's a glimmer of light, or rather radiation, thanks to the quirks of the quantum world. This radiation is not just a theoretical concept, but a real phenomenon that has profound implications for our understanding of black holes and the universe. Now, you see, in the quantum realm, empty space isn't actually empty. It's a seething, bubbling cauldron of activity filled with what we call virtual particles. These are particle-antiparticle pairs that constantly pop in and out of existence, borrowing energy from the vacuum of space itself. This seemingly empty space is actually a dynamic and lively environment at the quantum level. It's teeming with what we call virtual particles, particle-antiparticle pairs that constantly pop in and out of existence, borrowing energy from the vacuum of space itself. These virtual particles are a fundamental aspect of quantum mechanics, illustrating the strange and counterintuitive nature of the quantum world. They're like fleeting ghosts in the cosmic machine, existing for such a short time that they almost defy detection. These particles appear and disappear so quickly that they are almost impossible to observe directly, yet their presence has significant effects on the fabric of space-time. But here's where it gets interesting. The interaction between these virtual particles and the intense gravitational field of a black hole leads to some truly extraordinary phenomena. When these virtual particle pairs form near the event horizon of a black hole, something extraordinary can happen. The immense gravitational forces at the event horizon can separate these pairs, with one particle being pulled into the black hole while the other escapes. Imagine one particle falls into the black hole while the other escapes into the vastness of space. This escaping particle now has no partner to annihilate with, becoming a real particle. And voila! This process results in the emission of radiation from the black hole, a phenomenon that was once thought impossible. The escaping particle now has no partner to annihilate with, becoming a real particle. And voila! This seemingly magical transformation is a direct consequence of the strange and wonderful rules of quantum mechanics. This, my friends, is the essence of Hawking radiation, named after the brilliant physicist Stephen Hawking, who first proposed its existence. Hawking's groundbreaking work showed that black holes are not entirely black but emit radiation due to quantum effects near the event horizon. It's a subtle but significant effect that demonstrates the interconnectedness of gravity and quantum mechanics, two pillars of modern physics. This interplay between the macroscopic world of gravity and the microscopic world of quantum mechanics is one of the most fascinating areas of modern scientific research. Over incredibly long timescales, this radiation can cause black holes to lose mass and eventually evaporate completely. This process, while slow, suggests that black holes are not eternal and that they have a finite lifespan. The concept of black hole evaporation has profound implications for our understanding of the life cycle of black holes and the evolution of the universe. It challenges the notion of black holes as eternal prisons and opens up new possibilities for the fate of matter and energy in the cosmos. The study of Hawking radiation and virtual particles also provides valuable insights into the nature of space-time and the fundamental forces that govern the universe. It bridges the gap between quantum field theory and general relativity, two of the most successful yet seemingly incompatible theories in physics. Researchers continue to explore these concepts, seeking a deeper understanding of the universe's most mysterious and powerful objects. The quest to unify gravity and quantum mechanics remains one of the greatest challenges in theoretical physics. As we delve deeper into the mysteries of black holes and the quantum realm, we uncover more about the fundamental nature of reality itself. The universe, with all its complexity and wonder, continues to surprise and inspire us. So, the next time you gaze up at the night sky, remember that even the darkest corners of the universe are filled with light and mystery, thanks to the incredible phenomena of quantum foam and virtual particles. The cosmos is a vast and wondrous place, full of secrets waiting to be discovered. And with each discovery, we take one step closer to understanding the true nature of the universe and our place within it. The journey of exploration and discovery is never-ending, and the wonders of the cosmos are always just beyond the horizon. So far, we've been talking about stellar mass black holes, those formed from the death throes of massive stars. But hold on to your hats, folks, because the universe has a knack for taking things to the extreme. And when it comes to black holes, that means supermassive black holes. We're talking about black holes with masses millions, even billions of times greater than our sun. These cosmic behemoths lurk at the centers of most, if not all, large galaxies, including our own Milky Way. They're like the gravitational anchors around which entire galaxies pirouette. Now, how these supermassive black holes form is still a subject of intense research and debate among astrophysicists. One leading theory is that they grow from smaller seed black holes, gobbling up surrounding gas and stars over billions of years. It's a cosmic feast of epic proportions. And there you have it, folks. We've journeyed from the formation of black holes from dying stars to the mind-boggling concept of Hawking radiation, and even explored the supermassive giants lurking at the hearts of galaxies. Black holes continue to captivate our imaginations and challenge our understanding of the universe. They remind us that the cosmos is a place of both breathtaking beauty and profound mystery, where the familiar laws of physics are pushed to their limits. Who knows what other secrets these cosmic enigmas hold, waiting to be unveiled by future generations of explorers and dreamers. Thanks for watching. If you enjoyed learning about black holes, don't forget to like, subscribe, and hit the bell icon for more mind-blowing content. See you next time.